As we solve systems of equations, we have two methods, substitution and elimination, or I often call that the addition method, because what we're doing in that method is we're adding equations together to remove variables. So the same applies when we're doing systems of equations that are nonlinear. They're a little bit more particular. When we do linear systems of equations, we can pretty much use substitution or addition on all of them. But when we have nonlinear systems of equations, then sometimes we have to make a decision. In this particular example, notice that we don't have like terms between the two variables other than the constants. In the first equation, x is to the second, but it's to the first in the bottom equation. Same thing with the y's. So if we were to do the addition method, we would not be able to make the x's cancel because we couldn't make them opposite without multiplying by a variable, and we don't want to multiply by any variables. And we don't want to have to square any sides or anything like that. It does not work to simply square each term. That would no longer be equal. So we can't make like terms that way. So if we don't have like terms, we're going to have to use substitution. So in doing that, we're going to isolate a variable in one of the equations. So let's isolate y in the second equation. Preferably, we want to use a variable that is to the first power. So y and x are both to the first power down here, so pick one to isolate. And in the other equation, replace y with 1 minus x. So the top equation, we would call x squared plus 1 minus x squared equals 25, replacing y with 1 minus x. Remember, we don't just square each term. We have to write 1 minus x times 1 minus x, distribute that out, and we would get 1 minus 2x plus x squared. Collect like terms. We have an x squared, another x squared, so that's 2x squareds, minus 2x plus 1 equals 25. So we just collected like terms and put the left in descending order. Now, since this is quadratic, x to the second, we want to get everything on one side, so take away 25 from both sides. So that's going to give us 2x squared minus 2x minus 24. And this one is going to factor. All three terms have a 2, so we can pull out our common factor. Take a 2 out of all three terms, and then the parenthesis factors. X minus 4 times x plus 3. Set each factor equal to 0. Well, that first factor, 2, that can't possibly equal to 0 because it's a constant. But to make the second factor 0, x would be 4. To make the last factor 0, x would be negative 3. Now remember what a solution is. It's an ordered pair. So we're going to have an ordered pair where x is 4, and we're going to have an ordered pair where x is negative 3. So we just want to find out what y goes with each of those. So like we've done in the past, we take those x's and plug back in. So here, we could plug into the top equations. One thing I would encourage you not to do is to plug the x back into the top equation because of the y squared. If we plugged it in place of x and then solve for y squared, we might end up generating an extraneous solution, a solution that doesn't work. So if either of the equations are linear, then let's use that one to plug our x back into. I'm going to use this one. Y is by itself, and y is what we're looking for. Y is 1 minus x. So if you tell me what x is, y is 1 minus that number. So for the first one, y is negative 3. For the second one, y is 1 minus negative 3. Well, minus a negative makes a plus, so y is 4. So that gives us two different solutions. And we could check that if we wanted to. We could substitute the first ordered pair into both equations to make sure it works, and we could do the same thing with the second. Let's quickly graph this one just to see what this looks like. If we graph x squared plus y squared equals 25, that is a circle centered at the origin with a radius of 5. If we graph x plus y equals 1, that's a line with a y-intercept of 1 and a slope of negative 1. So if we drew a line through that, we would get this. And notice we have 2 points of intersection. So our system of equations has two solutions. One is at 4, negative 3, and one is at negative 3, 4. Now, you're not going to be asked to graph these and visually find their intersections, but I wanted to do this just to demonstrate what it is that we're finding. We're finding the ordered pairs that work for both equations, and when we have things that are more than just straight lines, then we could have more than one solution. So in this case, we have two solutions. There could be instances where we have more than two, or that we still just have one. If we have a circle intersecting another circle, it could be that they intersect at one point, or it could be that they intersect at 2 points, or no points, or if we intersect at any ellipse with that, they could intersect twice, or they could intersect 3 times, or they could intersect 4 times, or they could intersect just 1 time or no times. Lots of different combinations of equations, of shapes, and the number of solutions. But we're not going to have to do any graphing. Our equations are going to tell us how many solutions we have. So let's go on to another one. Here we do have like terms between the two equations. Excuse me. So we could do the addition method, elimination, or I'm going to just do a substitution here. Notice this bottom equation says that y squared is x plus 3. Now notice that top equation has a y squared in it. So we could replace, instead of replacing y, we could replace the whole expression y squared with x plus 13. So in place of y squared, we put x plus 13. So we made a substitution. As long as we're replacing something and we know what that value is equivalent to, it doesn't have to be to the first power. It could be to any power, as long as these two match. This is a quadratic equation, so we're going to subtract 169 from both sides. Get a 0 on the right side, so that will give us x squared plus x 13 minus 169, that's negative 156. And then we need to see how that factors. Now, feel free to use the quadratic formula to solve that. I recognize here, and this is just talking through what my thought process is. I know x squared is x times x, and I know my signs have to be opposites. So if my signs are opposites, then these two numbers have to multiply to make 156, and they have to have a difference of 1. Multiply to make 156 have a difference of 1. So I know that 12 times 12 is 144. So what about 12 times 13? What is 12 times 13? Well, that is 156. Why did I pick 12 times 13? 12 and 13 are 1 apart, and when I subtract those numbers, I get 1. I might have started off trying 13 and 14 because they're 1 apart. But if I multiply those together, that doesn't give me 156. But 12 and 13 have a difference of 1, a product of 156. So we need a 13 here, a 12 here. 13 times negative 12 is negative 156. 13 minus 12 gives us the 1 in the middle, so that factors. So if we set each factor equal to 0, we would get x equals negative 13 for the first one, x equals 12 for the second one. So we have two x values. So the question then is, well, what are our y values going to be? So once we get the x's, we can plug them into either equation. Use the bottom one, because that's the closest to having y by itself. So when x is negative 13, we get negative 13 plus 13, which is 0. And if we take the square root of both sides, y is plus or minus 0. Remember, when we take the square root of both sides, we have to include plus or minus. Well, 0 can't be positive or negative, so really just 0 is. So when x is negative 13, that corresponds to y being 0. Now for our other one, if we replace x with 12, we get that y squared is 25. So if we take the square root of both sides, we have to include plus or minus, and the square root of 25 is 5. So when x is 12, we could get a positive 5, or when x is 12, we could get a negative 5. So in this one, we actually have 3 solutions. A negative 13 corresponds to a 0, 12 can correspond to 5, or a negative 5. So 3 different solutions. Notice we didn't draw the picture to figure out how many solutions there were. We got 2 x's, and once we had those 2 x's and plugged them in to one of the equations to get y, the number of answers we got for y told us how many solutions we would have. All right, if we take a look at this one, we again have like terms between the 2 equations, and this time I am going to use addition. Notice if we add these 2 equations together, the y squareds are going to cancel. And we could have done that on the previous one, but on this one, y squared minus y squared will cancel. 1x squared and another x squared makes 2x squareds. 25 plus 25 is 50. So by adding the equations together, we made one of the variables go away. So we can divide both sides by 2. If we take the square root of both sides, the square root and the square cancel, so x is plus or minus 5. If we take the square root of both sides, we have to include plus or minus. Only if we take the square root of both sides. If we just are asked what's the square root of 16, the answer to that is 4. But if we're taking the square root of both sides of an equation, we include plus or minus. So we're going to have at least one answer when x is 5, and at least one answer when x is negative 5. So to find out what that answer is, we're going to plug 5 in for x in either equation. I'm going to take the top one. Doesn't matter. And I'm going to replace x with a positive 5 and see what happens. So 5 to the second is 25. If we subtract 25 from both sides, we would get that y squared is 0. And if we take the square root of both sides, notice we get 0 for y. So when x is positive 5, we get y is 0. Now if we take that same equation and replace x with a -5, -5 to the second is 25. This is the same equation that we had there. So instead of showing all of the steps to get y again, if we already know how that equation comes out, that y equals 0, then just tell me that. We've already worked it out step by step once. Here, we don't need to redo it again, but y is 0, so when x is -5, y is also 0. So that gives us two solutions for this one. When x is 5, we only get one y. When x is -5, we only get one y, so two solutions. So let's do another type. Notice in this system, we don't have like terms, so we can't use the addition method. So we go back to substitution, and we're going to isolate a variable. Either variable we want, we're going to isolate. So I'm going to take the bottom equation, and I'm going to divide both sides by x. So on the left side, the x's cancel, and we get y is -8 over x. So in the top equation, we're going to replace y with that expression, -8 over x. Just changing y with that. So when we have a fraction raised to a power, we square the numerator. So -8 squared, or -8 times -8 is 64. X to the second power is x to the second power. Now we can clear our fractions. We have an x squared on bottom, so if we multiply everything by x squared, so multiply the left by x squared and the right, we get 20x squared on the right. On the left, we would do x squared times x squared, which is x to the fourth. X squared times the next term, the x squared on bottom, and that x squared would cancel. Let's show that. X squared times that, the x squared would cancel, leaving 64. This is not a linear equation, so we're going to get everything on one side. So subtract 20x squared from both sides. So that gives us a 0 on the right. And if we put the left side in order, we have x to the fourth minus 20x to the second plus 64. Now we could do this a couple of ways. This is not quadratic, but it is similar to a quadratic in that we have an exponent here. This exponent is twice as much. Or we could say that this variable part is this one squared. And then we have a constant. And when that happens, we can factor this directly. We could make a substitution, but notice that the fourth, we could call that x squared times x squared. Our signs have to be negative times negative to get a positive here and a minus in the middle. And then we just need to take 64 and find out what multiplies to make 64, adds to make 20. So 1 times 64 doesn't add to make 20. 2 times 32 doesn't add to make 20. 3 doesn't go into it, but 64 is 4 times 16. That adds to make 20. So now we have that factored. If we were to check, we would have x squared times x squared, which is x to the fourth. -4 times -16, which is positive 64. That would be minus 4x squared, and this would be minus 16x squared, which would make our minus 20x squared in the middle. Now we could either set each factor equal to 0, or we could factor the difference of squares. Factor those. Set all four factors equal to 0, so we would get that x is 2, x is -2, x is 4, and x is -4 when we set each factor equal to 0. So this time we have 4 different x's, and there could potentially be a different y, more than one y that goes with each x. So we need these x's and plug back in to get y. So if we have a choice, we want to pick the simpler one. So I'm going to pick this one because it involves smaller power. And because it already has y by it. Y is negative 8 over x. Y is negative 8 over x. So we can take each x, replace x with each of those, and that'll give us the corresponding y. So negative 8 divided by 2 is negative 4. So that gives us an ordered pair. Let's see, on the next one, if we take negative 8 and divide by negative 2, we get 4. So that gives us another ordered pair. The next one, replace x with 4. So that gives us another ordered pair. And then lastly, we get that y is 2. So for each x, we got just one y. So we have a total of 4 ordered pairs that are solutions to our system. So that's kind of a variation. Gives you a good assessment of different types of nonlinear systems of equations that we could solve and the different techniques that we would go about doing those.